Imagine, just for a second, that you're staring at this giant spreadsheet.
Like a really massive one.
Yeah, exactly.
Yeah.
It's just completely filled with raw data, and you're looking at like a single row. And it says a user spent 2,500 and they made 3 orders.
Okay.
Now, as humans, we look at that and our brains, they immediately start spinning a story. We guess like, oh, 2,500 over just 3 orders. That's a big spender. That means something.
Right. You instantly assign a persona to them.
Exactly. But a machine learning model, it doesn't understand meaning from raw numbers. It just sees digits. It doesn't inherently know that 2,500 is a lot of money or that 3 orders in a week is, frequent.
It's completely blind to context.
Yeah, totally blind. It needs interpretable signals. So raw data, as it turns out, is absolutely not model ready. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects.
Glad to be here for this one.
We know you listening already have, some Python under your belt. But today we are officially putting on our AI engineering mentor hats. We're doing a deep dive into lesson 6 of our SQL for ML Engineers series.
Which is titled, How Data Gets Transformed, Turning Raw Values into Model Features.
Right. And our goal for you today is to build a really highly intuitive mental model of how we actually translate cold, raw numbers into actionable meaning using SQL. And doing that before that data ever even touches a Python algorithm.
Yeah, because to build that mental model, we need to locate exactly where we are in the feature engineering pipeline, right? We've been building this sequence with you all. We start with tables, then we move to projection, then filtering, followed by joins, and then aggregation.
Right, we've covered all that.
Exactly. And that sequence brings us directly to where we are right now, which is transformation. And the core intuition, like the really big thing you need to hold on to today, is the difference between those last 2 steps.
Aggregation and transformation.
Yeah. Aggregation tells us how much happened. But transformation, that tells us what it actually means.
Okay, let's unpack that distinction a bit because I think it's crucial. If we look at aggregating data, getting all those totals and sums, it's a lot like pumping crude oil out of the ground.
Oh, that's a good way to look at it.
Right. You have this massive bubbling quantity of it, and it's valuable, sure, but it's entirely raw. You can't pour crude oil straight into a sports car and expect it to run.
No, the engine would completely choke.
It would be ruined. So transformation is, it's the refinery process. It's taking that crude oil and chemically altering it, refining it into high-octane jet fuel or gasoline.
So the machine learning engine can actually combust it and drive those predictions.
Exactly. We are essentially building that refinery today in this deep dive.
And in SQL, the primary piece of machinery inside that refinery is what we call the 5th SQL pattern.
The CASEWHEN statement?
Yes, CASEWHEN. Think of it as a conditional logic engine. It evaluates the raw data row by row, checks it against rules we define, and then assigns a new value based on the very first condition that turns out to be true.
I actually want to walk through how that logic engine runs, structurally. If we go back to our opening scenario, the user who spent 2,500.
Right, the big spender.
Yeah. We need to assign them a label. And in SQL, it's great because it almost reads like a plain English sentence. We literally write the word case, and then when total underscores spend underscore last 30 days is greater than 2,000.
Then output the label high value.
Exactly. LLC output regular, and we just wrap it up with ND.
It's elegant. That simple statement systematically converts a mathematical quantity into a behavioral category. And, you can apply it to literally any metric.
Right.
If a user made more than 5 orders, they become frequent. If less, they're occasional.
Yeah.
We are basically mapping business logic directly onto the raw data.
And that makes perfect sense for turning numbers into text categories. But there's this other concept we need to cover called one-hot encoding, which honestly seems to do the exact opposite.
Yes. It does go the other way.
Right. We take a text category like, say, a user's country, and we use this exact same case-when logic to turn it into numbers. For example, when country equals India, then 1 else 0. But wait, I have a question here. If machine learning models are supposed to be so incredibly smart, why do we have to dumb down a rich concept like India into a simple 1 or a 0 for them?
That's a really common question. It helps to remember what a machine learning model actually is under the hood,
Okay.
It isn't an encyclopedia that reads text. It is a massive, complex mathematical equation.
Yeah.
It relies heavily on matrix multiplication.
Oh, right. Math.
Yeah. You cannot multiply the word India by a numerical weight of 0.5. If you feed a string of text into an equation, the math literally throws an error and the whole training process just crashes.
Ah, so the model isn't like reading the country name at all. It's looking for a mathematical switch to flip.
Exactly, a switch. Transforming text into binary signals, ones and zeros, it bridges the gap between human language and machine math.
That makes sense.
By creating a specific column called, let's say, is underscore India, we give the model that mathematical switch. If the user is from India, the switch is a 1, and the model multiplies its learned weight by 1, activating that pathway.
And if they aren't?
It multiplies by 0, which completely neutralizes it. This process creates the feature matrix. And CASEWHEN allows us to build those matrices seamlessly right inside our SQL database.
Yeah, okay, so CASEWHEN is essentially this, like, universal translator. It turns raw numbers into human categories and human categories back into binary numbers for the algorithm.
It really is the workhorse.
But we can also use this logic engine to manage data that's already numeric, but maybe just, like, way too specific. Which brings us to the concept of binning.
Yes, binning. It is absolutely fundamental for handling ranges of continuous data. Take a feature like user age, right? User could be 18, 19, 20, all the way up to 100.
The way I conceptualize binning is it's like sizing t-shirts.
Oh, yeah, the t-shirt analogy is perfect.
If you run a clothing brand, you do not manufacture a custom shirt for someone who has exactly a 38.2-inch chest and then another completely different shirt for a 38.3-inch chest.
That would be a supply chain nightmare.
Completely chaotic. Dealing with that infinite continuous spectrum is impossible. Instead, you take that whole range of measurements, say 38 to 40 inches, and you just group them together into a single category called medium. You tame the infinite possibilities into manageable bins.
And we do the exact same thing with continuous data features in ML.
Right.
If we write the SQL, case when age is less than 25, then young, when age is less than 60, then adult, LC senior end, we have just binned an entire lifetime of exact ages into 3 neat categories.
I understand the convenience there, for sure. But as an AI engineer, doesn't the model lose precision if it doesn't know my exact age? Like, why would we intentionally hide data from the algorithm?
That's the counterintuitive part. Losing that hyper-specific precision is often the actual goal.
Really?
Yeah, because it prevents the model from overlearning random noise. We don't want the algorithm getting distracted by the behavioral difference between a 32-year-old and a 33-year-old.
Because that difference is probably just random chance.
Exactly. We want it to learn the broad, general patterns of an adult. But more importantly, binning protects the math from breaking when it encounters extreme outliers.
Oh, outliers. Like someone accidentally typing an extra digit into their birth year on a sign-up form.
Precisely. Think about a user who accidentally inputs their birth year as 1914. Suddenly you have a 110-year-old in your database.
Which is probably not your target demographic.
Right. If you feed the raw continuous number 110 into the model, the algorithm's mathematical weights will heavily skew trying to account for this massive unexpected value. It completely warps the equation.
But if that data passes through our binning logic first,
the SQL simply sees that 110 is greater than 60 and smoothly categorizes them as senior.
wow.
The outlier is neutralized before it ever reaches the Python model. The system stays stable.
Okay, so binning protects us from wild, crazy numbers. But there is a much more common data issue that will honestly crash a model even faster than an outlier.
Total emptiness.
The total emptiness. Real-world data sets are never pristine. Like, never. Users skip questions on forms, tracking pixels fail to fire, databases drop connections. We end up with these massive empty spaces.
Missing values are a daily reality in data engineering. And in SQL, those missing values manifest as NOL.
So if I have an NEL in my data, I'm basically handing the algorithm a missing puzzle piece. And if it's trying to do matrix multiplication, a NUL isn't a 0, it's a void. It will throw an error. So what does this all mean for the model? If a value is missing, does that just mean there's a system error we need to delete so it doesn't break our pipeline?
Deleting missing data is a massive trap that beginners fall into.
Really?
Yeah. This raises an important question, and here is a critical ML engineering insight for you all. NUL is information.
Wait, how can the absence of data be information? That sounds like a paradox.
Think about an e-commerce database. A user creates an account, so they exist in the users table. But if you query their total underscore spent column and it comes back as NULL, it usually doesn't mean a server crashed somewhere.
What does it mean?
It means the user navigated your site, browsed around, and intentionally bought nothing. That behavior, the act of not purchasing, is an incredibly valuable signal for predicting their future behavior.
Oh, I see. It's like a detective noticing the dog that didn't bark.
Yeah.
Right. The silence itself is the actual clue. But we still have the mathematical problem. The model can't multiply by silence. So how do we translate that behavioral clue into an actual number?
We use a SQL function called COALESCE. The syntax is pretty straightforward. COALESCE, then open parenthesis, column name, comma, default value, close parenthesis.
Okay, so we'd write COALESCE total underscore spent, comma, 0.
Yes. This tells the database engine. Check the total spent column. If there is a number there, keep it. But if you encounter an NLL, intercept it and replace it with a clean 0.
And a 0 is a mathematically valid weight. The equation can actually process it.
Exactly. The model explicitly sees that $0 were spent. And beyond just replacing values, engineers often use COALESCE to create a completely separate binary feature flag.
Like another one-hot encoded column.
Yeah. You might create a column called missing underscore phone underscore number with a 1 or a 0. Because sometimes a user refusing to provide their phone number on a form tells the model way more about their privacy habits than the phone number itself ever would.
That is fascinating. All right, so we've built the foundation of our refinery. We've used CASEWHEN to categorize data and encode text. We've binned continuous numbers to handle those outliers. We've used COALESCE to turn empty voids into actual mathematical signals.
The crude oil is getting cleaner.
It is. And now we shift gears. We stop just cleaning data, and we start combining it to create what I like to call super signals.
Ah, derived features.
Yes, derived features. Feature engineering becomes a really creative process here, right?
It does. A derived feature basically takes two separate raw pieces of information and mathematically combines them. And it does this to reveal a deeper truth about user behavior that, frankly, neither raw number could show on its own.
The classic example, I think, is dividing total spent by total orders. In SQL, that is as simple as total spent divided by total orders, as average order value. But why is that division so crucial?
Because simple aggregates lack context. Ratios like average order value or spending per day or clicks per session, they normalize user behavior. They level the playing field so the model can see true intent.
Normalizing behavior. Let's visualize that for a second. Imagine user A spends $100 over the course of 10 different orders.
Okay.
And user B spends $100 in a single order. If the model only looks at the raw total spent aggregate, it just sees $100 for both. It treats them as identical customers.
But their behavior is completely distinct. One is a highly engaged browser, buying cheap, low-risk items constantly.
Right.
The other makes rare, high-ticket purchases. By feeding the model the derived ratio, the average order value of $10 versus $100, the algorithm suddenly sees the structural difference in their shopping habits.
It's like putting glasses on the model.
Exactly. In production environments, these derived ratios almost always carry way more predictive power than the raw totals.
So we've derived these powerful ratios. But now we run into a completely different mathematical problem. The problem of scale.
This is a big one.
Let's say we feed our model a feature like age, which naturally tops out around 80 or 90. But right next to it, we feed it total spend, which could easily reach like $10,000.
That disparity in scale is super dangerous. Algorithms are highly sensitive to the physical size of the numbers they process.
Right, because it's just math.
Yeah. If one feature is measured in tens and another is measured in thousands, the algorithm's math might automatically assume the larger number is thousands of times more important, simply because it takes up more numerical space.
To fix this, we have to force all our features to speak at the same volume, essentially. We need them all to sit on the exact same scale, usually strictly between 0 and 1. And this process is called min-max scaling.
Yes. The mechanism behind min-max scaling is basically about establishing a floor and a ceiling for your data. And then you calculate where a specific user sits as a percentage between the two.
Let's actually walk through the math of how we do that, because, it looks a little intimidating at first glance, but it's deeply logical. The formula is the value minus the minimum value divided by the maximum value minus the minimum value.
Let's apply it so it's less abstract. Imagine the absolute minimum any customer has ever spent is $0. That's our floor.
Okay.
And the maximum any customer has ever spent is $1,000. That is our ceiling. The distance between them, the range, is 1,000.
Okay, so now a specific user comes along and spends $500. We take their value, 500, and subtract the floor, which is 0. So we still have 500.
Right.
Then we divide that by our range of 1,000. 500 divided by 1,000 is 0.5.
And boom. That user's spending behavior is now represented as 0.5.
It's brilliant.
If they spend $1,000, 1,000 divided by 1,000 is 1.0. If they spent nothing, it's 0.0. We have successfully mapped a massive dollar amount onto a tight scale between 0 and 1.
I always think of it like a teacher grading tests on a curve.
That's a great analogy.
It ensures that you're comparing different users fairly. You don't want a massive $10,000 purchase to completely drown out the mathematical weight of a tiny but incredibly important number, like a 0.5% click-through rate.
Right, they need equal footing.
By scaling both features down to a 0 to 1 range, the 10,000 and the 0.5% get an equal voice in the algorithm's ear.
And scaling stabilizes the training process, too. It ensures the mathematical weights adjust smoothly rather than violently swinging around to accommodate massive numbers.
Makes total sense.
And, while we're standardizing data, we also use basic SQL functions to clean strings and dates. We might use lower, passing in the email column, to ensure john@email.com with a capital J is recognized as the exact same account as john@email.com in all lowercase.
Oh yeah, case sensitivity will ruin your day. Or we use date math, taking current date and subtracting sign-up date to get days since sign-up. We turn a static, unhelpful timestamp into a dynamic number that actually represents user loyalty.
Absolutely. All of these transformations, the conditional logic, the binning, the scaling, the string formatting, they're incredibly powerful. But there is a massive trap here.
Oh boy.
An ML danger zone known as feature inconsistency.
This is where models literally go to die in production.
It really is. If the transformation logic you apply to your historical training data is even slightly different from the logic applied to your live production data, your model's performance will completely collapse. Training must equal inference.
Let's visualize how that collapse happens for the listeners. Imagine you train your model today. In your SQL query, you define a high-value customer as someone who spends over $2,000. The Python algorithm spends hours learning all the subtle behavioral patterns associated with that $2,000 group.
And it learns them perfectly. Then, 6 months later, the model is deployed live in inference. But a different data engineer writes the production pipeline, and they decide, hey, high value should actually mean spending over $5,000.
It's an absolute disaster. The live data pipeline is feeding the model a completely different reality than the one it learned. The model starts making wildly inaccurate predictions because the very definition of the signals changed beneath its feet.
This is exactly why doing the transformation layer directly in SQL is an industry best practice.
Right.
By writing these transformations as SQL views or materialized tables, you create a single source of truth. The exact same SQL query guarantees consistent feature logic, whether you are pulling a massive batch of historical data to train the model or streaming live data to make a real-time prediction.
Which brings us to the final assembly. When you combine all these concepts, the final SQL feature query is, honestly, remarkably elegant. It reads like a blueprint for intelligence.
You start your query with a simple select user id.
Then you pull in the raw aggregate. Total spend last 30 days. Then the logic engine drops in. Case when total spent is greater than 2,000, then 1LC 0 and its high value flag.
Boom! We just created our one hot encoded meaning.
Next, we handle the messy reality of the real world. COALESCE total orders last 30 days, comma, 0 AS total orders clean.
The voids are filled.
And finally, we forge the super signal. Total spent divided by total orders asked average order value. All of those mechanisms exist in one beautifully structured, consistent query that outputs a perfectly clean, model-ready mathematical matrix.
It really is the culmination of the entire feature engineering pipeline. The raw data has been fully refined.
So to summarize our deep dive today, transformation is the definitive moment where raw data becomes a signal and AI can actually understand. We explored the core SQL tools to make this happen.
We covered a lot of ground.
We did. We used CASEWHEN to build conditional logic and bin continuous outliers. We used COALESCE to harness the behavioral information hidden inside missing data. We used division to create normalized derived features and min-max scaling to ensure the model's math stays balanced.
The crude oil is now high-performance fuel.
It is. But looking ahead, we have a really critical bridge to cross. So far in this series, we've built robust feature tables out of static snapshots of data.
True.
We've assumed time is just, standing still. Now we have to add the most complex and arguably the most important dimension of all, time.
Introducing the temporal dimension shifts everything. Behaviors aren't static, they sequence and they evolve.
Get ready, because the exact title of our next lecture is How Time Shapes Behavior, Creating Time-Based Features SQL for ML Engineers L7. Make sure you have your mental models from today totally locked in for that one.
Before we close out this session, I want to leave you all with a final thought to ponder on your own. Throughout this discussion, we have been hard-coding our logic. We literally type the rule. Spending over $2,000 makes someone a high-value customer.
Right, it's hard-coded.
But the real world is entirely dynamic. What happens to your perfectly engineered feature logic when the economy fundamentally changes? When major inflation hits and the real-world definition of a high-value cart suddenly shifts from $2,000 to $3,500?
Oh, wow. That's the ultimate challenge, isn't it? The world moves, but the SQL query is just carved in stone.
Exactly. How does an AI engineer handle a transformation rule that naturally goes out of date? Do you manually rewrite and redeploy your SQL queries every single time the inflation rate ticks up? Or is there a more sophisticated, dynamic way to build your refinery so it automatically adapts to the changing nature of the crude oil?
That is a phenomenal engineering problem to chew on. Think about how you design a logic engine that tunes itself. Because remember, your goal isn't just to format a spreadsheet. Your goal is to build a system that genuinely understands the evolving meaning behind the numbers. Keep refining those signals, and we will see you next time.